math shop? Yes, this is Christine. Yes. What? Euclid! Shh. Can't hear anything. Yes. Oh, yeah, we can help you with that. Okay, no problem. Well, you know. Not really. Okay, thanks for calling. Bye.
Christine, look! We've got our posters.
That's great, Kanwal, but listen, we've got an emergency on our hands. Somebody just called and said that they need to know what's the largest number that they can write using only 3 digits and any mathematical operation.
Largest number using 3 digits.
Right.
I've got it.
Really, already? Great. The largest number using only 3 digits, what is it?
Oh, about 50 centimeters high.
Oh, my sides. Okay, in case you haven't guessed it, you're watching The Math Shop, and we're here to help you with a puzzling, fascinating study of mathematics. And today, we're going to focus on exponents, scientific notation, and something called bedmass. But what about that problem, Kanwal?
All right, the problem is the largest number we can write using 3 digits.
Right.
Okay. Some people would think 999 was the answer. But numbers are only part of the language of mathematics. There are also operations.
Operations are the way that numbers relate or act on one another. The most common of these are addition, subtraction, multiplication, and division.
So we could write a number like this: 9 plus 9 plus 9, or 99 times 9, or even 99 divided by 9.
Right, except that a fraction would make our number smaller, and we're looking for something bigger.
Maybe you've already figured out that there is another way to go, and that is the use of powers or exponents. So I have 9 times 9 to the power of 9.
Exponents take us into large values very quickly. Euclid, calculate, please. Thank you. And what about this? Great. That last one's huge. Millions of digits, in fact. And that's our answer. Ta-da! Exponents win. 9 with the exponent of 9 to the 9th power is the largest value that we can write using 3 digits and any operation. Okay, Euclid, take a break.
Exponents allow you to express a number used as a factor a certain number of times. For example, 2 times 2 times 2, expressed as 2 to the 3rd power, has a value of 8. Whereas 7 times 7 times 7 times 7 times 7, expressed as a power, is 7 to the 5th power. Now, 7 to the 5th power has a value 16,807.
You could say that those little expressions sure pack a lot of punch, huh?
Right. Now, exponential notation is composed of 2 parts, a base and an exponent. The exponent is this raised number that tells you how many times the base is used as a factor. Usually, we read this as b to the power of x, but there are a couple of important exceptions. 4 to the 2nd power, but you will also hear people say as 4 squared.
May I demonstrate?
Please do.
Good. Okay. Our base is 4. So we have 1, 2, 3, 4. Now, 4 to the 2nd power means that the base is used as a factor twice, or 4 blocks 4 times. 1, 2, 3, 4. This is the same way we calculate the area of a square. The sides of a square are equal, so we use the length as a factor twice. Side times side, or the length of the side squared.
The other exception is when we say, for example, 4 to the 3rd power or 4 cubed.
Right. 4 times 4 times 4. And this is the same as calculating the volume of a cube. Side times side times side. And that's why an expression to the 3rd power is often called cubed.
Let's look at the concept of exponents. 2 to the power of 1 is just 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. Now what happens when the exponents decrease? Well, if I decrease, I'm going to divide by 2. So 2 to the power of 0 is 1. 2 to the power of negative 1 is 1/2. 2 to the power of negative 2 is 1/4. As you see, when the exponents increase, the value increases. As the exponent decreases, my value decreases. There are a number of rules that apply to exponents. Euclid, please. The multiplication rule, the power rule, the division rule, the rule for negative exponents, and the rule for 0. Let's expand on the rule for multiplication first. If I have 2 to the power of 5 times 2 to the power of 3, I get 2 to the power of 8. Now, if the bases are the same, when you multiply, you just add the exponents. Let me expand this. I've got 5 2's times 3 2's. As you can see, I've got 8 2's, which is 2 to the power of 8. So the multiplication rule is, if the bases are the same, add the exponents. Now let's take a look at the power rule. When a power is raised to an exponent, for example, 2 to the power of 5, all raised to the power of 3, I just multiply the exponents. This is 2 to the power of 15. Once again, let me expand this. I've got 2 to the power of 5, and I've got 3 of those. Like multiplication, I can add these exponents, and I get 2 to the power of 15. So the power rule is, when a power is raised to an exponent, multiply the exponents. Let's take a look at the rules for division now. 2 to the power of 5 divided by 2 to the power of 3 equals 2 to the power of 2. Whenever you divide, if the bases are the same, you subtract the exponents. Let me expand this for you. I've got 5 2's in the numerator, and I've got 3 2's in the denominator. And of course, these cancel, these ones too, and these ones too. I'm left with 2 2's in the numerator, which is 2 squared. And that's the division rule. If the bases are the same, subtract the exponents. Now, let's take a look at the rules for the negative exponents. If I have 2 to the 3rd power divided by 2 to the 5th power, and once again, my bases are the same, I just subtract the exponents, this equals 2 to the power of 3 minus 5, which is negative 2. But let me expand it again. I've got 3 2's in the numerator and 5 2's in the denominator. And of course, I'm going to cancel these. This time, I'm left with 1 in the numerator and 2 2's in the denominator, which is 2 squared. Notice these two are the same. So I have 2 to the power of negative 2, which is equal to 1 over 2 squared, which again is equal to 1/4. So the rule for negative exponents is, a power with a negative exponent is the same as 1 over that power with a positive exponent. Now let's take a look at the rule for 0. If I have a question, 2 to the power of 3 divided by 2 to the power of 3, once again, bases are the same. I subtract the exponents. I get 2 to the power of 0. But when I expand this, I've got 3 2's in the numerator and 3 2's in the denominator. And again, I'm going to cancel these. This time, I've got 1 in the numerator, 1 in the denominator, which is equal to 1. So 2 to the power of 0 is equal to 1. And that's the zero exponent rule. Any number with a zero exponent equals 1. Now, all of these apply only when the bases are the same. But if the bases are different, well, then we must expand them. For example, 2 to the third power times 3 to the second power. I can't add the exponents, but now I must expand it. This is 8 times 9, and my answer is 72. So I hope you've got the idea of exponents now, because you need them to handle your next topic, scientific notation. And I think that Christine, where's Christine?
I'm right here, Kanwal.
Oh, I see. Thank you. Christine, is that a field trip?
Yes, Kanwal, I'm outstanding in the field because I wanted to take some measurements. In technical and scientific work, we often measure things that are very large or very small. For example, if I measure the brightness of the sun, and kids, don't try this at home. Okay, Euclid, give me a reading. I get a reading of 3 octillion candle power, give or take a few melted candles. Now, supposing I wanted to compare that with the brightness of, say, this candle. Euclid, can you help me out here? Thank you. At a distance of 1 meter, I get, surprise, 1 candle power. But suppose the candle were further away. Hit it, Euclid! The candle is further away now. Suppose that it's as far away as the sun. It's still putting out as much light, but not as much as getting into my scanner. In fact, it's only... well, only a few hundred nanofemto candle power now, if there was such a thing as nanofemto. Anyway, it's very, very small. And if I wanted to see how many times brighter the sun is compared to my little candle, my problem would look something like this. It's a lot of numbers. And the answer would be long, too, if I could keep all the zeros straight. Well, that's why we have something called scientific notation. Kanwal?
Scientific notation is based on exponents, specifically powers of 10. Let me show you. A number to be converted to scientific notation is first rounded off to 3 significant digits. Let's take a look at the measure of the sun's brightness that Christine did for us. 3 octillion, 14 septillion. Well, that's a lot of zeros. When we round it off to 3 significant digits, it becomes 3 octillion, 10 septillion. Now, the number is then rewritten in a 2-part expression. The first part is a number greater than 1 and less than 10. Let's move the decimal point from here all the way to here. This gives us 3.01, which is then multiplied by 10 raised to a certain power, which in this example is 27. Now, we get this 27 from the number of places I moved the decimal point. Therefore, our expression in scientific notation is 3.01 times 10 to the power of 27. Now, large numbers have a positive exponent. Very small numbers have a negative exponent.
Well, that's how we write scientific notation, Kanwal. But how do we work with those numbers? And what about my comparison between the sun and the candle?
Good point, Christine. But your comparison requires division. If you don't mind, I'd like to work with multiplication first. Okay. So let's look at another example. Let's use muffin.
Get your hands off my cat.
Relax. Just a little calculation. Let's first find out how many hairs does muffin have. Could you scan?
Okay. Right, Euclid? How many hairs does muffin have? Calculate, please.
Ah, 29,110,000. And the average length of hair on muffin. In meters, please. Okay, decimal 028 meters. Now, if we multiply the number of hairs by the average length, we will have the total length of hair on muffin. But let's do it with scientific notation. Muffin has 29,110,000 hairs, which is 2.91 times 10 to the 7th. Times her average length of hair, which is 0.028 or 2.8 times 10 to the negative 2. Now, I multiply the first numbers, 2.91 times 2.8, and I multiply the powers of 10. 10 to the 7th times 10 to the negative 2. Now, I get my expression as 8.148 times 10 to the power of 5. I round this off to 3 significant digits, which is 8.15 times 10 to the 5th. Now, if I express this in standard form, I get 815,000. And so, Christine, that's how many meters of hair Muffin has.
Oh, well, no wonder I need a lint brush. Okay, Kanwal, let's get back to my problem now with comparing the sun to the candle.
Oh, yes. In other words, division using scientific notation works like this. Change each number to a scientific notation. The numerator is 3.01 times 10 to the power 27. And to get my denominator in scientific notation, I move my decimal point 23 spaces to the right to get a number between 1 and 10, which in this case is 6.67 times 10 to the power of negative 23. Now, I divide my first numbers, 3.01 divided by 6.67 times 10 to the 27 divided by 10 to the negative 23. When I divide my first numbers, I get decimal 451 to 3 significant digits, and I subtract the powers of 10, which gives me times 10 to the power of 50. Now, to write this in scientific notation, I move my decimal point 1 place to the right, and my power of 10 decreases by 1, which gives me 4.51 times 10 to the power of 49.
Right. So as you see, now we have a measurement of how much brighter the sun appears than that candle. But before we move on from scientific notation, there is one other point that we should look at, and that is using scientific notation with a calculator. Kanwal?
Let's do a multiplication example. 2.44 times 10 to the power of 12 times 5.23 times 10 to the power of 15. Now, we can use the simplest of calculators by multiplying the first numbers. 2.44 times 5.23 equals 12.7612 times 10. Now I add the powers of 10, which is 27. I must adjust the first expression to be between 1 and 10 and 3 significant digits. So I move the decimal point 1 place to the left, and I adjust my power of 10 by adding 1. So my answer now is 1.28 times 10 to the power of 28. Now let's do this example using the double E key, which allows us to easily enter scientific notation. If your calculator has all the keys we mentioned last time, chances are it has the double E key as well. Enter 2.44, the double E key, followed by the power of 10, which is 12, times 5.23, the double E key, and the power of 10, which is 15, equals, and I get 1.2761 times 10 to the power of 28, which rounded to 3 significant digits is 1.28 times 10 to the power 28. Okay, let's do a division example. 1.23 times 10 to the power of 9 divided by 3.90 times 10 to the power of 23. I enter 1.23, the double E key, followed by 9, and then divided by 3.90, the double E key and the 23, equals, and I express my answer as 3.15 times 10 to the negative 15.
Our next segment is on problem solving. Now, problems are a major problem for students. That's why we've made this incredibly good-looking and useful poster.
One thing to remember about math problems is that they are no different from the kinds of problems we all face in everyday life. And we use a wide range of techniques to solve them.
Right. Would you believe that many of the strategies we use for something as simple as getting to work on time can also be applied to mathematics? Now, to show you exactly what I mean, here's what I found when I took the microcam out onto the street and asked people about their problems. Euclid, run clip 1.
My problem is traffic. I usually take Oak Street, but if the traffic's bad, I'll swing over and take Granville. Or I may try another way, like Canby.
When it hits 38th cell. See, stock prices go up and down all the time, but what I need to know is when those variations get big enough to notice. So we use a graph. And the graph alerts us to any big swings.
But of course, no 2 days are the same. So I listen to the traffic reports to get more information about where the tie-ups are.
My sister asked me to make her wedding dress. I said, fine, I'd love to. But then I thought, well, maybe I should make a simpler version of it first, just to make sure it turns out okay.
And I look for patterns. For example, on Mondays and Fridays, I found it's better if I just leave 5 minutes earlier.
Some of my recipes take a lot of preparation. I may need to marinate something overnight, for example. So I decide when I'm going to serve something, then work backwards to see when to start preparation.
Can I go now? I'm going to be late for work.
Thanks, Euclid.
Right. Many of those problem-solving strategies, such as working backwards and looking for a pattern, can be used to solve math problems too.
Right. So now let's try a math problem and see how it goes. It starts like this. What's this?
A handshake.
Right. So this is how the problem goes. If 15 people go to a party and everyone at the party shakes hands with everyone once, how many handshakes are there? Now, how would you attack that problem, Kanwal?
Well, there are a number of steps that our poster shows that will help us solve the problem. First, you think about the problem. What do you have to find? Then you assess the information, list the important facts and the keywords. And then think about a strategy. Pick one, work backwards, draw a diagram, use a formula. Try something, apply your selected strategy, and then check it out. Did you solve the problem? If not, then go back. And then once you've done it, no problem. Let's try a strategy. How about simulating the situation? Euclid, give me a party of 15 people shaking hands. Oh, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, it's possible, but it's happening too fast for me to count. Let's try a different strategy. Euclid, draw a picture, and let's use a dot for each person, and a line for each handshake. Whoa, too many lines. Let's try something else. How about a table? Not that kind, Euclid. We want a chart that'll help us find a pattern. That's good. Number of people on the left, number of handshakes on the right. For one person, no handshakes. For two people, obviously one handshake. For three, we have 3 handshakes. Let's combine our strategies. Let's bring in a diagram. 4 people, 6 handshakes, 5 people, 10. You know, I think there is a pattern here. This increased by 1, this increased by 2, this by 3, this by 4. Okay, Euclid, finish it off. So, it seems there were 105 handshakes at that party. By the way, is there a formula for this, Euclid? N times n minus 1 over 2. Fantastic.
Solving problems often means doing some calculation, and one place where people trip up is not paying attention to bed mass.
That's right, bed math. It's nothing to do with Christmas.
Right, but here's a present for you anyway.
Thank you.
Now, BEDMAS is an acronym. It stands for the order in which you perform operations. When you have a complex expression, it makes a big difference which operations you do first. And while some calculators will remember that for you, not all are that smart.
B is for brackets, E for exponents, D for division, M for multiplication, A for addition, and S for subtraction. Let's do an example using BEDMAS. 2 to the 5th minus 8 divided by 4 plus 2 brackets 3 plus 1 all to the power of 2. Let's do bracket first. Here I have 3 plus 1, which is 4, to the second power. Next I do exponents. 2 to the 5th is 32. And 4 to the second power is 16. Division is next. 8 divided by 4 is 2. Next I do multiplication. 2 times 16 is 32. And finally, when we come to addition and subtraction, we just go from left to right. 32 minus 2 is 30. 30 plus 32 is 62. Let's see if I get the same answer if I ignore BEDMAS and just go from left to right. 2 to the 5th is 32. Minus 8 is 24. 24 divided by 4 is 6. 6 plus 2 is 8. 8 times 3 is 24. 24 plus 1 is 25. To the second power is 625. I certainly did not get the same answer as 62. So remember, whenever you're doing a question with the order of operations, remember BEDMAS.
Well, Kanwal, that's great. But as Euclid is pointing out, there's one problem you can't solve. We're out of time.
That's no problem. Let's get out of here.
Okay, see you next time on Math Shop.
Bye.
Bye. Oh. Hello, Math Shop. Yes. Oh, great. So it worked for you then. 9 with the exponent of 9 to the 9th power. Yeah, I like that. Yeah, okay, right there. Yeah, I like that too. I love 9s. I don't know, ever since I was a kid, I just love 9s. Really. So what are you working on anyway? Oh, yeah. That's really... Mink farm. Wow. Wow, really? I never had a mink hot dog before.